So red, of course, is 2, green is 5, and orange is 25,000 plus or minus 5%. So you got to find the 5%, which is 1,250. So yeah, you'd subtract that, which is 23,750, to adding that 26,250. Is that what you had? Perfect. You ever see how they came up with that? How about going the other direction? What if I give you that the range on my resistor is 50,400 ohms to 75,600 ohms? Can you figure out what the color code on that resistor must have been? Perfect. To find the ideal value, we add the two together, the minimum and the maximum together, and divide by 2. Gives us 63,000 ohms. So the plus or minus would be how much? Well, we subtract that from either one of them is going to give us 12,600 ohms. So the next thing we have to do, now that we've got the plus or minus, the ideal value and the what we call the allowance. A lot of people call that the tolerance. It's actually an allowance. The tolerance is double that. The tolerance on this resistor is 25,200. But anyway, we have the ideal value and the allowance. We need to convert this into a percent. So blank over 100 equals 12,600 over 63,000. If you cross multiply and divide here, you get 20. 100 times 12,600 is going to be 1,260,000. Divided by 63,000 is going to be 20. Does that make sense? So what that's saying is that this is plus or minus 20%. So 63,000 ohms plus or minus 20%. So then on to our color code. What would the first band on our resistor be? 6, which is blue. Next would be 3, which is orange. The third band is the number of zeros, which is 3, so orange again. What's that?
I just need to go black for 0.
Oh, sure. Yeah, you'd have to go black, 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 and then you'd have 5 bands, and you can only have 3. Then, of course, the tolerance band of 20, none. Silver would be 10. You either leave it blank, or they sometimes will use a black for 20%. Again, that's usually, US is usually just left blank for 20%. You guys feeling pretty comfortable about the resistors when I've done them in the lab? So we've looked at what our main point dealing with those is that tolerance, that allowance. We can have a relative tolerance, which is what you saw with that plus or minus 5%, 10%, 20%. That's a relative tolerance. You know, plus or minus 5%. Or we can have an absolute tolerance, where it was plus or minus an exact value. That last one, it was 12,600 ohms to start out with before we converted it into a percent. There are advantages to having errors expressed in either way. Though those are not necessarily the only way that we can express. For you guys in electronics, you will generally use what's called a bilateral tolerance. What we've done up here, both of those are forms of a bilateral tolerance. One's just relative and the other's absolute. There is something called a unilateral tolerance. And that might look like something like this. Rather than dealing with electrical components, I'm going to deal with an actual dimension of an object. And let's say that on a print for this, on a schematic for this piece, it is labeled 0.750 inches plus 0.000 minus 0.010 inches. What does that mean? Well, it means, go ahead. Exactly. That means that piece, in an ideal world, we want it to be exactly 750 thousandths. We want it to be exactly 3/4 of an inch. But we know the world's not ideal, but because of the way it's going to be used, it cannot be larger. But it could be a little smaller. This creates a range of, take our 0.750, we can subtract the 10 to give us 0.740 inches, or 740 thousandths, up to, we could do the 750 plus 0, which is 750 thousandths. So there's the range it gives us. Now that is the exact same range we would get if we had to add them together and divide by 2. The center of that range is 745 thousandths, plus or minus 0.005. That gives us the exact same range. So why would we express it like this instead of like this? Yeah, this is what we want it to be. This is describing what we really desire. Think of it this way. Let's say that we have a manufacturing process. We're going to make this part. And the machine that we have that's going to make this part is capable of producing parts to within plus or minus 0.003 of an inch. If the print comes to me as the person setting up this machine labeled like this, I'm just going to set the machine to 745 thousandths, aren't I? And it's going to go, of course, 3 less is going to be 742. To 3 more is 748. I'm just going to set it 745 thousandths and let it go, and it's going to be within that range, well within that range. But I'd rather not have them down this small. I'd rather have them closer to 750. So if it comes to me labeled like this, I'm going to set that machine and say, hey, my machine never goes more than 3 thousandths off. So I'm going to set my parts at 747. So now it's going to give me parts from 744 up to 750. Does that make sense?
So
So
it only has to deal with what's the most accurate for what you
yeah, what is describing what we really want to use the part for? If you guys were in automotive or machining, we talk about clearance fits and interference fits, where you have two parts that fit together. And you guys do have to deal with it a little bit because you got a lot of stuff that plugs in and things like that. But you're not necessarily going to be looking at creating the plugs. You're not going to be manufacturing the plugs. They're going to be done before they get to you. But it's when two parts go together. Some parts are designed so let's say they have to go together. Most of the plugs you use are designed with what they call slight clearance. There's actually going to be a hole in here and a pin here that slides over usually. The outside here is designed with a slight clearance, so there might be like a couple thousandths of an inch so that can go in and out without binding real bad. But these pins in here, usually there's like a spring clip in there, so that goes in and holds it in place, and that's what holds it in place. But there are some of those plugs that don't have that spring clip. They're designed with what's called an interference rather than a clearance. And what that is this piece here is actually slightly larger than what it's going into. And generally it's designed with a little bit of a beveled edge on it then. So that when you push that in, it actually forces its way in there. And the fact that it's slightly larger is what holds it in. So it's extremely tough to get it back out. Like I said, for you guys, you're not going to be manufacturing those, but it's good to understand that if you've got something that is an interference fit, if you plug it in, make sure you're ready for it to be plugged in. Because trying to pull it out, you're most likely going to do damage to it.
When you're calculating this, it doesn't take you a fact into the working, does it?
It does not take, if it's a heated process, it doesn't take any into account any sort of shrinkage or cooling, anything like that. One of my areas that I worked in engineering was industrial efficiency and quality control. And that's one of the tricks of setting up test equipment. Like I had worked with Weather Shield. I did a lot of consulting work. And one of the consulting jobs I did was with Weather Shield up here. What is it now? Quantico. What do they call it? Not Quantico, but Quanix, they call it now. They had parts that were extruded aluminum for the frames of their screens. They'd come off the line and get cut. Well, they're testing them. They're still pretty hot when they tested them. So they would typically shrink 3 or 4 thousandths of an inch as they cooled. So they had to compensate with their test gauge for that few thousandths of an inch. Well, they ran into problems. There were people that were running that test gauge. It never explained to them how it worked and why it worked that way. So they would take parts that were, because they had a green range on the gauge. Here's your gauge. There'd be a green range here. This is just a needle that spun around. So if that needle spun around and was in the green range, that part was good. Well, over here, the part was too short. Over here, the part was too long. So if it was in the red, they tossed it out. Well, some of the people that were running that gauge realized, okay, if the needle's over here, it's too short, we got to toss it out. But if the needle's over here, it's too long, and they realize if you set it off to the side for a while and let it cool, and plug it back in 10 minutes or so when it's cool, that needle might be in the acceptable range. Well, the problem was that gauge was calibrated for it being hot, for it being a few thousandths longer. So, yeah, it may have tested out on the gauge, but it was still too long. So then they did have they were having problems with screens that were being produced and being sent out and couldn't get them into the windows. You know, they've got that little spring so that they can, the emergency exit, so you just pull the little tabs and they pop out. They wouldn't pop out or they couldn't get them popped in because they were slightly too large. And it's amazing how little clearance they have on those when they're taking them in and out.
I suppose clearance for airtight stuff would have to be insanely small.
Yeah, it is. A lot of those have rubber gaskets and some sort of either an O-ring or a mechanical spring ring that seals up a lot of the gap in it. But yeah, there is some pretty tight tolerances there. And most of those are a double gasketed system. So it's either set up like this, or this is going into, so plugging into a surface like this. Usually there's an O-ring here that wraps around that seals into this surface. Then there's usually another one here that seals onto this surface. So you get that double seal. But yeah, there's a lot of stuff that goes into the tolerancing and stuff for that. Okay, so what we want to talk about now is we want to look at combining measurements that have these tolerances on them. Let's say we have two measurements. So let's say we've got that 750 thousandths of an inch plus or minus 5 thousandths of an inch. And we need to add to that another measurement plus or minus 620 thousandths of an inch, or 620 thousandths of an inch that's plus or minus another 5 thousandths of an inch. First of all, these tolerances, are those absolute or relative? Careful. Those are absolute. Relative would be if it's listed as a percent. So when we are talking about adding or subtracting measurements, we need to deal with absolute errors. I am going to perform whatever operation I'm asked to perform here. It's addition, so I'm going to add those measurements. So 1.370 inches. Over here, with my absolute errors, whether I'm adding or subtracting, I am going to add the errors. So 0.005 and 0.005 is 0.010. 5 thousandths and 5 thousandths makes 10 thousandths. So this new, the result of that addition is going to be 1.370 inches plus or minus 10 thousandths of an inch. So what if I have measurements that are given as relative? You know, plus or minus 1% there. Let's say I'm going to add to it 720 thousandths plus or minus 0.8%. What we have to do is we have to find the absolute error. This is a relative error.
So then you just gotta find the
1% of the 0.450. You got it. If we cross multiply and divide there, 0.0045. So it's 0.0045 inches here. And then we have to find the 0.8%. That's 0.8 over 100 of 720. So we cross multiply and divide there. It's going to be 0.00576. So we're adding, so we're going to add the numbers. So 1.170 inches. And again, whether we're adding or subtracting, we would add the errors. So it's 1.170 inches plus or minus 0.01026 inches. Now, if the original numbers were given as relative tolerances, relative errors, we would want to convert those back to relative. We wouldn't want to give an absolute error on our answer. So we're going to have to do blank out of 100 is 0.01026 over 1.170. So 100 times 0.01026 divided by 1.17. It's 0.877, we're going to call that. Probably call it 0.88%, most likely. So that's as a percent because it's over 100. So this is going to be 1.170 inches plus or minus 0.88. We'd round it off to for a percent, 2 decimals. Does that make sense? So if we were subtracting, let's say I have 1.240 inches plus or minus 0.75%, and I'm going to subtract from it 0.780 inches plus or minus 0.9%. What am I going to get as a result? Give it a shot. See what you come up with. You want to convert it back into a relative, since it's given as a relative. So your first step with the errors is to change the percents into an absolute, right? So you find 0.75% of the 1.24, which is 0.0093. What you come up with? Oh, you just added the percentages?
Yeah, then I...
Yeah. Okay. You've got to actually convert each of them into an absolute first. So then we do the same with the 0.9%. 0.9 over 100 equals blank over 0.780. Cross, multiply, and divide, you get 0.00702. Now I'm going to stop. Anybody have questions on where either of those two numbers are?
Yeah, where did you come up with the 0.009?
Okay, so it's 0.75%, so that's 0.75 over 100 equals blank over, that's out of the 1.24. We'll cross multiply 0.75 times 1.24, then divided by the 100, 0.0093. So let's cross multiply and divide. So that gives you that one. Same here, it's 0.9%, so it's 0.9 over 100 equals blank over the 0.78, cross multiply and divide, give me the 0.00702. So now over here, I subtract the numbers. 1.24 minus 0.78 is 0.460. What do I do with the errors? I always add the errors. Perfect. So I add those up, I get 0.01632 inches as errors, plus or minus. Everybody okay with how I got this number here? Any questions? I just added those two together. This, because I'm subtracting, I subtracted those two numbers. Just remember, the errors are always added, whether we're adding or subtracting. And now I have to convert it back into a relative error. So blank over 100 equals the error 0.01632 over the result, the 0.460, and I'm going to cross multiply and divide. 100 times the 0.01632. Yeah.
For converting that top number to a decimal, I got a different number.
This one?
Yeah.
So 0.75 times 1.24 divided by 100. Okay. You just try to change this to a decimal and get 0.0075?
I divided first.
Okay, gotcha. So we cross multiply and divide there. 100 times 0.01632 divided by 0.46. 3.55, we'll call it. Really? I suppose we're subtracting, so when you're subtracting, the errors always do get larger. So we ended up, this is 0.460 plus or minus, of course that's inches, plus or minus 3.55%. Does that make any sense? When we are multiplying or dividing, we add relative errors. So if I have 2.3 amps plus or minus, let's do this. This is plus or minus 3%. And let's say I'm going to multiply that by 2100 ohms plus or minus 10%. Well, I'm going to multiply the numbers, 2.3 times 2100, which is going to be 4,830. I'm going to add the relative errors. 3% and 10% is 13%. You're always adding the errors, no matter what operation you're doing. If you're adding or subtracting, you've got to work with absolute errors. When you're multiplying or dividing, you work with the relative errors. But no matter what operation you're doing, you're always adding the errors. So let's say, and I'm going to leave the units out of it for now just to keep this simple. Let's say we have 4.5 plus or minus 0.09 times 3.2 plus or minus, let's see here, 0.032. So this is multiplication here. First thing I've got to do is I've got to find the absolute errors, or the relative errors. These are absolute. I got to change those into percents. So how do I change that into a percent? Percent is out of 100, so it's blank out of 100. It's 0.09 over 4.5. So 100 times 0.09 divided by 4.5. 2% error. So that's 2, so that means this is plus or minus 2%. Does that make sense? That's just working with our percents. So then what are we going to do for this one to make that a percent? Oops, bottom one. You had the right idea though. 0.032. There you go. Over 3.2 exactly. Cross multiply and divide. This is going to be 1. So that's plus or minus 1% as a percent. So now what are we going to do with these numbers? Careful. Those two are multiplied. 4.5 times 3.2. Since we're multiplying, we multiply those numbers. 14.4. Plus or minus, the percents do get added. 2% and 1% make 3%. Now, this was given as an absolute error to begin with. We should probably convert them back to an absolute error. So 3%, 3 out of 100, blank over 14.4. Cross multiply and divide, you get 0.432. So this is 14.4 plus or minus 0.432. Whatever the units are on this. Any questions? Okay. So this is in the 12 packet. Page 264 to 265. 1 through 20 is dealing with these errors and combining errors and converting from relative to absolute and back again, and then combining measurements with errors. So I'll give you guys the last 13 minutes to get a start on that. Like I said, tomorrow there is a quiz, so when you get to after lunch, come on up and we'll do the quiz if you guys don't have people in the lab. Otherwise, if you do, I'll just send the quiz with you and you can finish up and bring it back to me. But I'd prefer to get in a lecture tomorrow if we can, because I kind of want to wrap up Unit 1 here at some point. We have that quiz. Then we're going to talk about efficiency for a couple of days, and some more resistivity and stuff like that in wires. Octal numbers. Yeah, it looks like we're going to be putting our test probably next week. I'd say Monday or Tuesday next week is where we're looking at our test.
We can use notes and stuff.
You can use your notes and your packets, and your books, since we haven't done anything out of the books, aren't going to be horribly helpful, but you can use your books or packets or notes.